In this presentation, I will talk about simple panel data models. The outline for this presentation would be to talk about the difference in differences model and then to talk about panel data model with first differences estimator. So let's consider first policy analysis with pooled cross-sections. So to provide the definition again, pooled cross-sections are when we have two or more independently sampled cross-sections in different time periods. These are not necessarily the same units between the two periods. So for example, we may have house prices of houses sold in two different periods, but they are not going to be the same house sold in both periods. So pooled cross-sections can be used to evaluate the impact of a treatment, event, program, or policy change. So the difference in differences model is very popular with when an event happens or a program happens or a policy change. This happens in natural experiments. And we will use the economic term treatment here to denote whether the units are treated or not, which means has the event or the program happened for them or not. And then we would have to have before and after period in order for us to be able to calculate these effects. So the difference in differences model would involve before and after comparisons for natural experiments to determine the effect of a treatment. So here's the basic setup of a difference in differences model, which shows the effect of a treatment in the after period. So here we would have a treatment being implemented for the treated units. So here treated would be equal to 1. And for the control units, there will be no treatment. So treated would be equal to 0. So again, in the setup, we need to have treated units for which the policy or the program or the change was implemented, and then the controlled units for which such treatment was not implemented. So data would be collected in the period after the treatment and before the treatment. So here we would have another variable with after equals 1 for the period after the treatment, and the period before the treatment after would be equal to 0. The interaction term would be treated times after, which would be equal to 1 for the treated units in the after period. So a differences in differences model would be the dependent variable would be regressed on this indicator variable for after, then the indicator variable for treated, and then I would have the after times treated as an interaction variable here. So this setup is very important that we have the before and after, treated versus control, and then the interaction between the two. And the difference in differences effect, delta 1, would be the effect of the treatment in the after period on the outcome y. So here we would call the dependent variable an outcome. So same thing as a dependent variable. So let's consider this difference in differences effect using two models. So here I'm going to show you the slow way in which we can calculate the difference in differences, but we typically will go the faster way. So suppose that we have this differences in differences model, like the way we introduced it on the previous slide. But here we would estimate one regression in the before period, so where after is equal to 0, and then another regression in the after period, where after would be equal to 1. So in the before period, this would be equal to 0, so therefore this would be equal to 0. And so we would just have here y equals beta 0 plus beta 1 treated plus u, because these terms here would drop out. And the coefficient beta 1 would be would show the differences in outcomes between the treated and the controlled units in the before period. So this is what this coefficient beta 1 will show, the difference between the treated in comparison to the controlled units, because that is the reference category here in this variable in the before period. So in the after period, what we need to do here is after would be equal to 1. So we would need to be collecting these coefficients. So if after is equal to 1, this plus this would be the intercept. And if after is equal to 1, then the coefficient untreated would be beta 1 plus delta 1. And so that's what the coefficient untreated is. So the coefficient here would show the differences in outcomes between the treated and the controlled units in the after period. And the difference in differences effect would be the difference between the two coefficients here. So here we would have the after minus the before. And so here we have the after minus the before, and that would be delta 1. Now notice that this coefficient here is already a difference between the treated and the controlled units. That's the definition of this dummy variable. And here is already the difference of the treated and controlled units that's in the after period. And so now we're taking the second difference, which is between the after period and the before period. So this is what we're doing here. The difference in difference effect would be the difference in outcomes in the treated and controlled units in the after period and the treated and controlled units in the before period. So another way in which we can calculate exactly this model is to split it in the other way, which is instead of calculating and estimating before and after models, we would be estimating them for the controlled units and for the treated units. So here for the controlled units, treated would be equal to 0. So if this one is equal to 0, this one would be equal to 0. So for the controlled units, we would have y equals beta 0 plus delta 0 times after. So that would be the regression here. And delta 0 would be showing the difference in outcomes between the after and the before for the controlled units. So notice that this coefficient here is already a difference between the after and before for the controlled units. So here, when we have for the treated units, treated would be equal to 1. And so here we would have this would be the intercept because treated would be equal to 1. So we would collect this coefficient plus this coefficient. And then this would be equal to 1. So for the coefficient on after, we would be collecting this coefficient plus this coefficient. And that's what we have here for the coefficient on after. And so here, this coefficient delta 0 plus delta 1 would be showing the differences in outcome between the after and before for the treated units. And so the difference in differences effect would be the difference between the two coefficients, which is this coefficient here and this coefficient here. And that would exactly be, if you look at this would exactly be the delta 1, the same coefficient as on the previous slide. So here we took the difference in differences effect as the outcomes after and before for the treated units, and then after and before for the controlled units, and that's how we calculated that difference in differences effect. So again, now we took the difference the opposite way. First we took the after and before, and then we took it for treated and control. And what we had on the previous slide is we took it first on treated and control in the after period and then the before period, and then we differenced that. So here is the complete difference in differences model, and here we have, we would be estimating actually the complete model instead of the two separate models. And this delta 1 coefficient here would be the effect of the treatment in the after period. So if we want to know what is the outcome for the controlled units in the before period, so here treated would be equal to 0 for the control units in the before period, where after would be equal to 0, here we would have y bar 0 for the control, 0 period controlled units, and that would be beta 0. Why? Because this would be equal to 0, this would be equal to 0, and this would be equal to 0. So the only coefficient that we have is this one. So actually this here intercept would be the average value for the controlled units in the before period. So if we want to calculate the outcome for the treated units in the before period, we would just have this coefficient and this coefficient here for the treated. Otherwise, this would be equal to 0 and this would be equal to 0. So these two coefficients would drop out. So here the outcome for the treated units in the before period would be beta 0 plus beta 1. So continuing on, the outcome for the controlled units would be treated equals to 0. In the after period, after would be equal to 1. And so what would we collect is this coefficient plus this coefficient. So treated would be equal to 0 here. So we have these two coefficients. And then if treated and equals 1 and after equals 1, we would be collecting all of the coefficients. And this would be the average outcome for the treated units in the second period. So how we would calculate the difference in differences effect, we would be taking two differences. Here we would be taking the average outcome for the treated units in the first period minus the treated units in the before period. And here we would have the outcome for the controlled units in the after period, outcome for the controlled units in the before period. And then we would take the difference between the treated and the controlled units. So we could also take the interaction in different way by just replacing this term with this term. We could like switch the place of these two terms. And so here's what we have here. We could actually take in the after period, we could be doing the treated the outcome for the treated units minus the outcome for the controlled units. And then the same for the before period. We could have the outcome for the treated units minus the outcome for the controlled units. And then take the difference between the after and before, and that would be the same difference. So again, that's the difference between this one minus this one, and then you're doing this one minus that one, and then you take the difference of these two differences. Or you could do this one minus this one, and then this one minus that one, and then take that difference, which is actually equivalent to each other. Okay, to show you the same thing in a table that we have here. So here we would be putting before and after, and here we would have the controlled and treated units. And this is what we're going to find. If we have, again, the after equals 0 and the treated equals 0, if after equals 0, treated equals 0, we would just have the beta 0 coefficient. If after equals 0, treated equals 1, we would be collecting these two coefficients. Then if after equals 1, treated equals 0, we would be collecting this coefficient and this coefficient. And then for all of the after being 1 and treated being 1, we would be collecting all of the coefficients here. And now again, how we take that difference is here we take the after minus before, after minus before. And so then we could take the treated minus the control, and that's that value. Or alternatively, we could be taking the differences in a different way, which is taking the treated and the control. And so we would be taking treated minus the control here and treated minus the control in the after period. And then we could do the after minus before afterward. And then that would also be the coefficient delta 1. So again, we have two differences and it's our choice, if we are to take the after minus before and then the treated minus control, or the other way around. We would take the difference for the treated and control and then the after minus before. So let me give you an example for differences in differences model. So here we would have the treatment being a building of a garbage incinerator. So this is a waste treatment facility. So if it's built in a neighborhood, that could potentially lower the prices of the houses that are near the incinerator. So here we have two periods. We would have an indicator in the before period, which is y81 equals 0 for the year 1978, and indicator of y81 would be equal to 1 in the after period of 1981, after the incinerator was built. And here we would have treated units would be the houses near the incinerator, and controlled units would be the houses far from the incinerator. So here our price is the price of the house, and we would have data on the before and after year. So here we would have the before year and the after year. And here we would have the treated and controlled units, which means near the incinerator or not near the incinerator. And these are the values that we have as far as average house prices. So notice one thing, that houses near the incinerator and far from the incinerator have increased in the after period. So actually this value here for the controlled units is higher than this one. And this value for the treated units in the after period is also higher than the before period. So house prices have increased in the second period for both types of houses. Now, house prices near the incinerator were lower in the before period. So if you notice here in the before period, if you're near the incinerator, the house price was lower than if you're far from the incinerator. But that difference actually even increased in the after period. So the houses that were near the incinerator had even lower prices. So the question that we have here before us is, did building of the incinerator lower house prices, or this outcome variable R price? So here's how we're going to do the difference in differences effect using two models. So let's estimate this model where we have the house price, and then we have dummy variable for the before and after, near the incinerator or not. So that's the treated variable, that's the before and after. And then we have the interaction term between them. So we can estimate a regression in the before period where y81 equals 0. And so if this is equal to 0, this will be equal to 0. So here we have the house price equals beta 0 plus beta 1 times near the incinerator. And so this coefficient beta 1 would be showing the differences in house prices for houses that are near and far the incinerator in the before period. And then doing the same thing for the after period, where y81 equals 1. So if this is equal to 1 and this is equal to 1, we would have two coefficients. We would have two coefficients here for the intercept, and we would have two coefficients here for the near the incinerator. And so this coefficient here, beta 1 plus delta 1, would be showing the differences in house prices for houses that are far and near from the incinerator in the after period. So that's this coefficient here. And the difference in difference effect would be the difference in the two coefficients. So it would be this coefficient here in the after period and this coefficient here in the before period. And if you substitute these, if you subtract these, that's going to be exactly the delta 1 coefficient. So here we have taken the difference between near the incinerator and far from the incinerator. So this is the treated units in the before period, and then the treated versus the controlled units in the after period. And then we would take the difference between the after period and the before period. So this is what's happening here if we estimate the two regression models. Here we have in the after period, we have this is the regression model. So, and in the before period, this is the regression model. And here we have near the incinerator, that's the treated variable. And here we have that in the after period, house prices near the incinerator were $31,000 lower compared to prices for houses that are far from the incinerator. In the before period, actually the house prices for near the incinerator were $19,000 lower compared to house prices that were far from the incinerator. So we see again that that difference is actually larger in the after period. So taking the difference in differences effect, we would do this coefficient plus this coefficient minus this coefficient, but because that second coefficient is a negative sign, then we would have this coefficient plus basically 19,000, and that would be minus $12,000. So the prices for the houses near the incinerator would be about $12,000 lower than the prices for the houses far from the incinerator after the incinerator was built. So notice again that these coefficients that we have here, these are actually average prices. This is the average price for houses in the after period for the controlled units, for the ones that are far from the incinerator. If you sum these up, this will be the prices for the houses that are near the incinerator in the after period. Likewise, these are the house prices uh, for houses that are far from the incinerator, the control group, in the before period. And if you sum up these coefficients, this will be the house prices of the houses near the incinerator in the before period. So again, we have taken the difference here first between near and far from the incinerator, near and far from the incinerator, and then the after minus the before period. So now let's do it the other way. So here is the same model, but here instead of calculating the estimating the model from after and before, we would have far from the incinerator. So here near the incinerator would be equal to 0, and then we would have oops, this is the houses that are near the incinerator. So here near the incinerator would be equal to 1. So what we would have here is that if they're near the incinerator equals 0, this term would drop out, this term would drop out. So we just basically have this term plus this term. And then if we have near the incinerator equals 1, then we would have all of these terms accumulated here. So this coefficient here would show the difference in house prices in the after period versus the before period for those that are far from the incinerator. And here, this coefficient would show the differences in house prices between after and before um, for those houses that are near the incinerator. Okay, so then the difference in difference effect would be the difference between the two coefficients. So this coefficient here minus this coefficient here. So notice that we have delta 0 plus delta 1 minus delta 0. So these two would cancel out. So we would have delta 1. So what we have accomplished here is we have taken the difference in the other way. So we first took it before and after for the treated, for the control and the treated units. And then we took the difference between the treated and the controlled units. And that's how we calculated that difference. So looking at the regression output, here we have for houses that are near the incinerator, these are the treated ones. And here, houses far from the incinerator, these are the controlled ones. And here we have the dummy variable for the after period. So here we have these two coefficients. So basically we have that for houses near the incinerator, houses prices were about $7,000 higher in the after period compared to the before period. And for houses that are far from the incinerator, actually house prices were about $19,000 higher in the after period versus the before period. So now, if we take the difference of this coefficient minus this coefficient, here we would be taking the treated versus the control, treated versus the control. And if we subtract these two numbers, that minus $12,000 would be exactly the same effect than if we took the difference the opposite way. So again, here we took the after versus before for the treated units, the after versus the before for the controlled units, and then we took that difference between the treated and the controlled units, and that's how we found this effect, the difference in differences effect. So notice again that all of these results as far as average house prices, we can again see these in the uh, table for the average prices. This again is the house prices for the treated units, for those that are near the incinerator in the before period. And in the after period, you have to just sum up this and this coefficient. That would be that house price. And here, this is the house prices for in the before period for houses that are far from the incinerator. And if you want to get the after period, we would need to sum up these two coefficients, and these would be the average house prices in the after period for those that are far from the incinerator. Okay, so finally, the difference in differences model, we can estimate it using the data. So the numbers in the table show the average house prices for the treated units, the houses that are near the incinerator, and the controlled units, houses that are far from the incinerator in the before and after period. And here we have the before and after period. Here we have the treated and the controlled units. And if we actually look at these average prices, we could actually put all the numbers in here. And so again, these are, we can see that this is the average price for houses in the before period for the controlled units. This is in the after periods for the controlled units. This is in the before period for the treated units, and the after period for the treated units. And so notice that if we do this value minus this value, it will be this value minus this value will be this value. And likewise, if we have this minus this would be this minus this would be this. And then we could take this difference either doing this one minus this one, or we can do this one minus this one, and that would be the same value here. And so again, that delta 1 would be the difference in differences coefficient, showing that house prices near the incinerator had about $12,000 lower prices than houses far from the incinerator after the incinerator was built. To show you all of these regressions in one table, this was the regression in the after period, and this was in the before period, so we went over this slowly. And here's for houses near the incinerator and houses far from the incinerator. Again, we went over these slowly. Now, no one would do these two regressions and then these two regression. Everyone would do straight the DID regression, and that's how we do it. We have a dummy variable for near the incinerator, one for the after period, and then the interaction between the two. And these are the coefficients that we find here. Now, notice that we actually can backtrack these coefficients to each of the models. So this coefficient here in the before period is exactly this one. And this one is exactly this one. And then for houses far from the incinerator, we have this coefficient equal to this one. And this one, of course, is equal to this one. So we actually have exactly the same coefficients. And we could actually obtain these coefficients here, these coefficients as well, from this regression by just noticing that this is actually for the treated units. So we need to be summing up two of the coefficients here. And this is for the after period. Likewise, we need to be summing up two of these coefficients together, and we would be getting the same results. So here, that difference in differences effect that we have here is the same as this coefficient minus this coefficient, or it's the same as this coefficient minus this coefficient. So it's the same coefficient that we have here of minus $12,000. So again, here we're concluding that house prices near the incinerator were $12,000 lower than prices far from the incinerator after the incinerator was built. However, this effect here was not significant. So our overall conclusion here would be that actually the building of the incinerator did not significantly lower house prices further from what they were lower to begin with before the incinerator was built, because that difference actually it's not significant. That's the conclusion here. So this concludes the difference in differences example. Now, shifting gears, let's talk about panel data models when we have two periods. So unlike the difference in differences model setup, here we actually have true panel data where we have a cross-sectional dimension I that would be people ID, firm ID, and so forth. And then a time series dimension t, which would be year, month, and so forth. And here the variables are y, it, x1 it, and x2 it. So notice here that we would actually be tracking the I and the t dimension from now on, because we again have panel data where both the I dimension and the t dimension would become important. So here we have example with 2 years of panel data. So here we have same units over 2 periods. Um, let's consider this being the model. Here we would have yt equals beta 0. Here we would have actually a dummy variable for the year. So this would be a dummy variable for the second period. So the first period would have a dummy of 0, and the second period would have a dummy of 1. And these would be the independent variables. And then this AI is a new thing that we see for the first time. We would call this an individual specific effect or a fixed effect. So they're unobserved time constant factors that are the same for each unit over time. So they're time constant or time invariant because look, there's no t subscript to it. So this does not differ based on the individual over time, but it's specific to this individual. So you can think something like that's the ability of the individual that contributes to their wages. So the ability is not observed, but it certainly influences wages. And that ability would not differ over time. Here, this UIT is an unobserved factor or the error term that would differ by units and by years. And so that's how we would have the model set up. One of the issues that happens here is that these individual specific effects or the fixed effects are time invariant, but they're unobserved, and so we cannot estimate them. We cannot estimate this model. And so we would need to find a way to actually eliminate this if we would like to estimate this model. So here's how we would do it. So here is the model described again. So if we have the model for the first year, what I would do here is this D year would be equal to 0 because that would be the first year. And everything else is copied from before. The model for the second year would have yi t plus 1. So notice it's not t, but t plus 1 for the next period. And here for the next period, that dummy variable would be equal to 1. And same thing, the x variables and the y and the u error term would be as of period t plus 1. But the one thing that would happen is this AI, the individual specific effect, would not change because it doesn't have the t subscript. And so what we can do here is we can subtract the model for the first year from the second year. And so we would have this one minus this one, and that's what we have here. We have this one minus this one cancels out. This one minus this one would be basically delta 0. And here we would have beta 1 times the differences in x, beta 2 times the differences in x, and here we would have u, the differences in u. So using the notation for first differences here, we would have delta yit. That would be equal to yit plus 1 minus yit. So this expression here could actually be abbreviated as delta yit. So that would be the differences between yit plus 1 and yit. So same thing for x1 and same thing for x2 and same thing for u. So now we can actually estimate this model, and we would call that we would estimate the first differences for this model. And this model does not include the individual specific effect, AI, and actually this model can be estimated by OLS. And this fixed effect was differenced out because it does not vary over time. So basically when we took the first differences, that's how it actually went away. So let's consider this to be our data set. So here we have panel data, and how are we going to take first differences? So with panel data, we have data for individual number 13, individual number 17, and individual number 18. So NR would be the ID for the person. Year, we have 2 years of data, 1980 and 81 here. And here we would have wage, hours, education, and experience, and they would be in the number. These would be in the number of years. And in order for us to difference, we would be using the terminology delta wage. So that would be, we would be calling this D wage. And so that would be the wage in 81 minus the wage in 80. So how we would do this is this number minus this one, it would be this one. This number minus this one would be this, and this difference minus this one would be this one. So we would be taking for each individual the second period minus the first period. So notice that we cannot take a difference between this one and this number because they belong to the different individuals. So we cannot take this difference. And these, we have these dots, which means missing values, because we cannot, with 2 periods of data, we can actually only calculate one difference. We can't calculate the difference, a second difference like that. And so same for the hours. So one thing that happens here for education is these people had 14, 13, or 12 years of education, but they did not increase their education. So if we take the difference, this one minus this one is a 0, this one minus this one is a 0, and this one minus this one is a 0. Likewise, everyone in the sample continued working, so this person added 1 more years of experience, this person added 1 more year of experience, and this person also added 1 more year of experience. So if we do this one minus this one, that's a 1, and that's a 1, and that's a 1. So what happened is that the first differences of education all had zeros, and of experience all had 1. Now, that didn't have to happen. You know, somebody might have gotten more education, but in the sample, no one did. And so therefore, these variables that are time invariant like that, or they change in very deterministic ways over time, what happens is that when we take the first differences, they are basically a constant. And one of the problems is that we cannot have a variable like that in our model because we would have perfect collinearity. So we cannot estimate a model like that. And so such variables cannot be included in the model here. We would need to have only the variables here, the differences for the variables that vary over time. So here's how we are going to estimate these models. So here we would have a panel data model for wages explained by the hours worked. And here we would have panel data model, which would be the wage in period IT. Here we would have dummy for the second period, and here we would have hours, and this would be AI, the individual specific effect. Here we would have the model for the first year. It would include AI, the individual specific effect. And here for the second year, we would also have AI, the individual specific effect. So notice that these models cannot be estimated because of this unobserved AI effect. So instead, what I would show you on the next slide is models without the AI, just to kind of make a point. But we really shouldn't be estimating models that have this individual specific effect. So the correct way to do it is actually to difference this and then calculate data wage regressed on delta hours, and that would be actually the model that we estimate. Again, this model is called first differences because we have this period minus previous period. You could take a second difference, say 2 periods ago, but first differences is the most common way. And so first differences, first differencing eliminated the individual specific effect, and now the model can be estimated by OLS. So let me show you all of these variations of models that we have here. Here we have model that has both periods in it. So here we are ignoring that we have panel data. And here we have hours wage regressed on hours, and that's the coefficient that we have here. And here we have wage regressed on hours as well as a dummy variable for the second period, and that's this period here. That's this coefficient here. And we can also estimate these two models just for the first period and just for the second period. And these are the coefficients here. Again, this is not a valid way to estimate the models for the first and the second period because, again, these individual specific effects need to be included in here, but I have not included them. But the reason why I estimated all of these models is to show you that actually none of these coefficients are significant except for this one. And for this one, actually, the magnitude is rather small. So because this is the model for the second period, how we would interpret this coefficient is that for the second period, if someone worked 1 hour more compared to other people cross-sectionally, right, they would be getting 1 cent lower in wages. So this is like a cross-sectional interpretation. The model with the first differences shows delta wage regressed on delta hours. And here what we have is that this coefficient here is larger. It's 0.035. And so the way we would interpret this is important. Here we have the same individual changing from 1 year to the next. So this is more the dimension over time. So if the number of hours for one person over time increased by 1 hour, then they would be getting 3.5 cents lower in wages. So notice that this coefficient here is interpreted over time for the same person, whereas here, say this coefficient, that was interpreted across the individuals for the second period. So here in this particular case, not always, but in this particular case, we have stronger significance and stronger effect and significance of this coefficient. So here also note that in this particular case, we actually have the R squared increases. So this model actually has a better fit. So the R squared is explaining 7.4% of the variation. So again, if we have panel data, this is how we need to estimate this panel data model using first differences estimator. So to end this, let's talk about a few review questions. So first of all, describe the difference in differences approach. What are the key variables that need to be included? What does the difference in differences effect measure? And then describe the first differences estimator for panel data models with 2 periods. So thank you for watching.